In this example, we're asked to derive the equations of motion for the 2 degree of freedom system that's shown here in the figure. It's got 2 degrees of freedom because we need 2 coordinates, x and theta, to completely describe where everything is in the system at any instant in time. The system is made up of block A, which is able to move along a smooth horizontal plane, a bar which is pinned to the block at A. The bar is thin, homogeneous, and there's a spring connecting the block back to ground, a dash pot connecting the block back to ground. Again, our goal is to find the 2 differential equations in terms of the generalized coordinates of x and theta. We'll start out with the FBDs for the 2 parts. The forces that are acting on the block, we have pin forces AX and AY. Have a normal force in here. We have a spring force, dash pot force. The spring, the force is K times X in magnitude. X is measured from the unstretched state. And when X is positive, that is to the right, the spring is stretched, the force X to the left. Same way here for the dash pot force, Cx dot. Moving over to the bar, Newton's third law says we have equal and opposite forces. So AX to the left, AY down. We have a weight force of mg. I'll call the center of mass of that g. And what I'm going to do is use for my coordinates in both kinetics and kinematics, x to the right and y up. So writing down the Newton-Euler equations for the 2 parts here, let's look at block first. If I sum forces on the block acting in x, I have the dash pot force and the spring force acting to the left. I have AX acting to the right. And that's equal to the mass times the acceleration. The acceleration is just x dot double dot because the block is moving along a straight path in the x direction. For the bar, we'll also sum forces in x. Summing forces in x, we have a minus AX, and that's the only force, so that's equal to MAGX, that is the x component of the acceleration of the center of mass. Summing forces in y, we get minus AY minus MG is equal to MAGY. And by some moments about G, recalling that this is the angle of theta here, that the force AX is going to have a moment arm of L over 2 cosine. The moment about G is going to be in a counterclockwise direction. That's the same direction as we assume for the positive sign conventions for theta, so that's a plus. Same way here for AY. It's going to have a moment arm of L over 2 sine theta, and it will have a positive SIGN sign that goes in front. So this is IG theta double dot, and for a thin homogeneous bar, IG is equal to 1/12 mL squared. So this is going to be my equation 1, 2, 3, and 4. Our goal is to reduce those down to 2 equations. We have a system with 2 degrees of freedom. We're going to need 2 differential equations. However, before I leave this, note that it may have been tempting for us to do a summation of moments about A on the bar. The reason for this is that AX and AY point through A, so that would give us a very simple, clean a moment equation. Unfortunately, if you sum moments about A, you cannot set that equal to the mass moment of inertia about A times theta double dot. Why is that? Well, it's because A is not the center of mass, and A is not a fixed point. And without those 2 possibilities, we are stuck with using G. Before I move on to the rest of what needs to be done, what I'm going to do is rewrite these equations just a tad, just to make it more easy to see what we want. Equation 1 I'm going to write as AX is equal to MX double dot plus CX dot plus KX. I'm going to write equation 2 in just a very slightly different form, where AX is equal to minus MAGX, and equation 3 I will write AY as being minus MG minus MAGY. Two things I'm going to do. I'm going to combine equations 1 and 2. 1 and 2 will say that MX double dot plus CX dot plus KX is equal to minus MAGX. If I combine equations 1, no, let me change my mind on that. If I do equation 2, equation 3, and equation 4. Equation 4 is that moment equation up there. So I'm going to have a minus M L over 2 cosine of theta times AGX. That's the first term there. AY is going to be minus MG minus MAGY times L over 2 sine theta. And on the right-hand side, that's IG theta double dot. So we're getting close. These two equations, which we'll label those as 5 and 6, are close to what we want. We have two differential equations. The unfortunate thing is we have embedded in these AGX and AGY. So we can't stop yet. What we need to do is just get it in terms of x, theta, and the time derivatives of those. What we need to do is look at kinematics. What I'm going to do is use the rigid body equation that relates the acceleration of g, the center of mass of the bar, back to the acceleration of NA of that bar. So I say the acceleration of g is a vector, is equal to the acceleration of A, plus the angular acceleration of that bar, crossed with the vector which extends from A to G, minus omega squared RG with respect to A. Again, the notation here means that those two position vectors need to extend from A to G. The acceleration of A we don't know. Acceleration of A is going to be in the x direction, and we're calling that x double dot. That's this term here. Alpha is theta double dot k, where k is the unit vector in z. The vector which goes from A to G, that's an L over 2 sine theta in the I, minus L over 2 cosine theta in the J. And then the omega squared, that's theta dot squared, and again, A to G is L over 2 sine theta I minus L over 2 cosine theta J. So I do my cross products and I combine terms together. In front of I get x double dot. I get an L over 2 cosine theta times theta double dot. I get a minus L over 2 sine theta in front of theta dot squared. That's all in front of I. in front of j. I'll have an L over 2 sine theta times theta double dot. I have a plus L over 2 cosine theta, theta dot squared, in front of j. This may look like not much progress, but it's quite good. This is the expression that we need for the acceleration of g y component. And this is the expression that we need above for the acceleration of g in the x direction. So what we need, actually I need to do is maybe zoom this in just a little bit so I can see more of my equations, because what I want to do is to combine these equations with the kinematics. So equation 5 here is going to be mx double dot plus cx dot plus kx is equal to minus, in fact let me extend this just a little bit, minus mgx double dot plus L over 2 cosine theta double dot minus L over 2 sine theta theta double dot, and that is going to be everything there on the right side. Equation 6 is going to be minus ml over 2 cosine agx, again, is equal to x double dot plus L over 2 cosine theta double dot minus L over 2 sine theta theta dot squared minus mg minus m agy, and agy we said was equal to L over 2 sine theta theta double dot plus L over 2 cosine theta dot squared, and that gets multiplied by L over 2 sine theta. And that on the right hand side is equal to the 1/12 ml squared theta double dot. We can reduce these equations a little bit. They're quite a mess, and we really can't avoid that. But we can take the first equation here, and we can write that as m plus m x double dot minus ml over 2 cosine theta theta double dot, and I guess that's going to be brought over to the left hand side, so that becomes plus, and I'm going to have an ml over 2 sine theta times theta dot squared plus cx dot plus kx is equal to a 0. Equation coming from equation 6, when I combine things together, what I'm going to get is, in front of x double dot, I'm going to get make sure I do this right, ml over 2 cosine x double dot. My theta double dot, I'm going to have a 1/12 ml squared coming from the right-hand side already. I'm bringing over to that same side in a big M, L squared over 4 cosine squared of theta. I'm also going to have brought over to that side the same thing with a sine squared. And that is that. So please leave room for theta double dot. On that side, I will also bring over a term here of minus ml squared over 4 sine theta cosine theta times theta double dot. And that's going to be added on to the same kind of thing with a plus sign. So this is ml squared over 4 sine theta cosine theta. And I think that there will be left over will be an mg L over 2 sine theta, like this. So that's it. A lot of effort and ending up with a set of equations which are quite involved. So these are our desired equations of motion. These EOMs in terms of x and theta. We'll talk about them later on in the course in a couple days. We'll talk about a better way to get to this end. This better way is going to be one that's based on an energy approach. And the energy approach will allow us to get the correct equations of motion and not have to deal with this set of internal forces of AX and AY. That was part of what we had. Part of the issues we had to deal with was that. We will still have to deal with the fact that the equations of motion do not simplify by doing a different approach. It's just the steps that it takes to get to that point.